Brilliant. Well, we're almost there. Today, we're going to be looking at entanglement measures. So the idea being, given a state, can we quantify in some way how entangled it is in the simple way of thinking that, for example, a Bell state appears to be very, very entangled. And a pure state is not entangled with, well, if, sorry, not pure state, all pure states. Just a state in the computational basis, for example, is not a state which is the tensor of different individual qubits. It would be very much unentangled. Okay, so let's recall a few things about density operators. So we saw that in the equality in the corollary to declining equality, that's the entropy of a operator is less than or equal to the logarithm of d, where d is the dimension of that space. So usually that would be d to the n. So usually, space on n qubits d is 2 to the n, and here we would have n. And we saw equality if and only if rho was 1 divided by d times the identity. So in this sense, we say that d rho is a completely mixed state. Now, in general, entropy, this von Neumann entropy of the density operator, is difficult to calculate because if you recall, to calculate it, we had to calculate the PIs, where rho which are the eigenvalues of our density operator rho, which requires basically diagonalization, or at least to factorize the characteristic polynomial. So that's a lot of work. And we can try approximating. So this one was then the minus the trace of rho. We could try approximating the entropy by using basically the table expansion of log x here. So that works the same for matrices. So we can do log of, log of 1 plus x is x plus minus x squared and 2 plus x cubed 3 minus 4, etc. So if we try sticking that in there, this will be log of 1 minus rho. So this would be then putting minus 1 minus rho into there, which gives us a minus out the front, and then we get 1 minus rho minus 1 minus rho squared divided by 2 plus. And now we make an approximation for this. by saying, well, these terms from here onwards are going to be kind of like less important into this sum. So this could be approximately equal to the trace of rho minus rho squared. And since the trace is linear and the trace of rho is 1, so we're just looking at this term here, we get 1 minus the trace of rho squared. So this is the rough approximation of the entropy, and this is called the linear entropy, which we're going to denote like this. And the linear entropy is much easier to calculate because we just have to square it and then sum up the trace. Now we know some things about this trace of rho squared because we proved them way back when. We proved that the trace, so proved that the trace of rho squared was at most 1 with equality if and only if rho is pure. Okay, so it's simply the Kepler of some state. There's other things that we could do. So if pi, let's just say pi b. So again, D is always going to be the dimension of the space that the rho is acting on. And the reason I don't put in 2 to the end, because we're going to see we're going to vary that dimension later. Okay, so it's just going to be D. And so if this is clearly bigger than equal to 0, so this implies that the sum of pi squared is bigger than or equal to 1 over D. So trace of rho squared is bigger than or equal to 1 over G. And with equality, if and only if rho is still here. Again, is equality if and only if all the PIs are equal to 1 divided by D, which implies that rho has only one eigenvalue, so it's simply 1 over D times the identity matrix. It's minimal polynomial is x minus 1 divided by D. So these two things, these two inequalities imply that if we now scale, in fact, so this is going to be a scalar multiple of this. So this implies that, so we define the linear correctly, so it should have done that before. So this is, let me write something here. So we say it just because I want that the linear entropy is always between 0 and 1. So this, the linear entropy, satisfies Right, so now we've got an idea of if this is a completely mixed state and somebody gives you a pure state, so let's suppose somebody gives you, so suppose we take a state, I'm to quantify it's entanglement. Well, what we want then is when we do the reductions down to just some of the systems, some of the particles, some of the qubits. What we want, if it's to be really entangled, is a high linear entropy, because this is going to be equal to 1. So this is going to be equal to 1 if and only if the reduced density operator is 1 divided by the dimension times the identity. So it's in a completely mixed state. On the other extreme, it's going to be 0 when this trace of rho squared is equal to 1, which corresponds to this reduced density operator being pure. So more or less, on a particular, so if we take on a particular position of the qubits, let's say into systems S and S prime. This is going to be S L of rho S will quantify the entanglement. Well, this will quantify the what I want to say here. This is going to be more like well, the mixedness against pureness. So let's have a look at examples. Let's just have a look at our classical example. If I take L state then rho be the Kepler of this pure state. S is going to be a system, the one particle system, the first qubit, and S, therefore, S prime is second qubit. And if we now calculate rho S, which is going to be tracing over S prime of rho, If we trace the pure state over rho, then we get up 1/2 0 0 plus 1. So indeed we get half the identity on the X system. So that's completely mixed up, reflecting the fact that there was a lot of entanglement between the first and the second qubit. Okay, it's completely like mixed up here. Okay? You couldn't get more mixed up. Well, in general, on a system of n qubits, we could take S to be any SS prime to be any partition of the n qubits. So on suppose on n qubits, with a S be subset size n. The average entanglement and this is going to be our entanglement measure of our pure state of our state psi. Well, what we want to do then is average out over the linear entropy. So we're going to go 1 minus the trace of rho S squared. So we took the linear entropy of our reduced operator. We're going to sum that over all S such that S has size n. And since we're doing the average, we're going to average out by all subsets of size n, which is 1 divided by n choose n. And I forgot to do the normalization. Damn. So of course I want to normalize by the number of states that I have, but the number of states now is in the M system. Once I've reduced down from to the S system, which has M qubits. So this is now going to be d divided by d minus 1 is going to be 2 to the n divided by 2 to the n minus 1. Okay, so that's just the linear, the something I've been averaging out, I get the average of the linear entropes over the subsystems of size. Okay. Now this we can slightly simplify because this 1 is summed over all the subsets, so this is simply 2 to the n minus 1 sum. Yeah, so I should say here, of course, that this rho is S is where rho is pure state size. Okay, so we define it, well, we could just define it for a pure state operator. Pure state density operator. It's difficult to have. I've got nobody to look at. Right. Now, another thing we have to remember from way back when. We have a pure state. Right. So the Schmidt decomposition. Implies this is orthonormal basis. Sorry. For the S system. Okay, so we showed in would have been, I can't remember when now, a long time ago. I think actually came on that we can do the Schmidt decomposition. We can find orthonormal bases of each of the systems such that this any state then can be written as the sum of lambda I, well, of course, the base with respect to the state. Like this. Okay, so we can write our state in this decomposition.
Wait, can you say again why the n2zem is not dividing the 1? Like when you sort of push the 1 over n2zem into the, like why doesn't it distribute?
Well, it's in both terms, but then, oh, sorry, I should have moved the sum in. Sorry, yes. Oh.
Oh, okay, yeah, okay.
That's good. Thank you, yeah. It's, yeah, absolutely. Yeah, it's just, well, something like everyone that might be choose any time, so.
Yeah, like the, yeah, exactly.
That's una vez más. Right, so we can use this we prove this implies that if we have rho equal to the Kepler, then rho S, the reduced density operator on the S system, we would trace out the S prime system and we get the sum of L lambda I bar IS, and likewise on the S prime system,
Is that really the case?
Sorry?
All right, yeah, okay. Yeah.
So this is interesting. This implies something interesting, because to be completely mixed, when you reduce down in general, you need all of the eigenvalues of your density operator to be exactly 1 divided by the dimension of the space. That's what we just saw in the last blackboard. But if this implies that if S is bigger than S prime, then rho of S cannot be completely mixed. It can't be completely mixed because it's got to have some 0 eigenvalues. Got these two things have the same, i.e. these have the same, i.e. so they have the same eigenvalues. 1. So looking for completely mixed states on the reductions, we can assume that, so if we are looking for maximum entanglement, we can assume the size of S is always going to be n, so m is less than or equal to n minus n. Okay, so m has got the most n divided by 2. So that's quite extraordinary because it's not immediately obvious, at least up to me, that you couldn't trace out on, say you had a 3-qubit state and you traced out on one, that you couldn't get completely mixed state. And apparently you can't. And that follows from the Schmidt decomposition. It's a very, very powerful observation. Okay, so now I want to look at 2 extremities of this entanglement measure. So we saw that this weighted this linear entropy here was somewhere between 0 and 1. So we take the average; it's still going to be somewhere between 0 and 1. So we know. Okay. I'll leave the definition of the entanglement measure up there, and I will keep it there. Yeah, so we saw. And we go and see what's happening in the extremity there, but let's just formalize that. So what happens if the entanglement measure should have probably said that this of course depends on which n you're choosing. So I should have said that this is for some n n being the number of qubits in the system. The system. So regardless of the n, if you get down to 0, then this state is simply the tensor product of n individual qubits. Well, for the entanglement measure to be 0, we need that all of these things are 0. So trace of rho squared is equal to 0 for all S. But of course, we just saw that this implies rho S is pure. And if you've got a pure state on every single reduction down to n systems, then this implies that this psi must be just a product of what a tensor. Okay, so you just cannot.
Wait, how far does the subscript for the size go up to?
Here.
Yeah, and up like in the statement of the lemma as well.
Yeah, I'm saying. So we're always on an n qubit system. So the big system's always got n qubits.
Yeah, okay. Yeah, it looked like an M, like the video feed is.
This looks like an n.
Yeah, choppy. Yeah. The Google Meet audio, video quality is kind of bad.
My n, this is an n because it goes on and on and on, and then the n's kind of go.
Okay. I mean, like it's difficult to see with like it was smaller than what you could see from the Google Meet quality.
Okay, I'll shut some of these applications. Sometimes that makes a difference. Oh, I'm going to shut Chrome there. Yeah, so it's just all that. It's just n qubits. Just everything's pure by every single reduction down to m states.
Wait, and why does this imply so quickly that?
Well, yeah, I knew it asked that. I mean, it's kind of obvious. I mean, think if you got a 3-state, and all the 2-state reductions are pure, then it's just something tensor, something tensor, something, right? Can't hear you, Adrian. I see you talking, but I can't hear you.
The fact that all the reductions are sort of multiplications, like how can you? I mean, I get the intuition behind it. Like it makes sense that it would be this, but it's sort of like, what's the argument?
Yeah, so it's something that as an exercise for us all to think about. Yeah, all the. Yeah, I agree. There's an argument missing there. You need to think about something, but it should be fairly straightforward.
Yeah.
Anyway, that's not what I wanted to talk about. Anyway, I was just doing that as a thing, just to see what happens at the other. It's the other extreme that I'm interested in. what happens when EM is 1? So clearly, I say clearly, this average is going to be 1. So clearly, EM is equal to 1. Well, that's equivalent to all of the things being completely maximum missed. So this is the so for every single subset we have this. So this is what did I say? The rest of the complete links. Nice. These are the same as the names. So now I want to prove a theorem about this then. So surprisingly, possibly, this is going to be if and only how we have a certain code. But before I get there, I want to slightly go back to our definition of errors that we could correct with our error correcting code. So let's just recall is a so we have all the weights of errors. Here I'm putting together the EI, dagger, EJ as one error because I'm just talking about the weight. Yeah, I'm not talking about correctable, I'm just talking about the definition, our definition of what the minimum distance meant for an error correcting code was that P times two correctable errors times P is C times P, where P is the projector of the projection. Now, at some point, we considered the case where the dimension of Q was simply 1, so we couldn't actually encode any logical information onto our code, but we still argue in the case of stabilizer codes that they were useful because then we could take subgroups. But you can in general, it doesn't have to be a stabilizer code, have the dimension of Q equal 1. So if the dimension of Q is 1, we insist on a pure code as we did for stabilizer codes, because otherwise the impure codes didn't make any sense. So we insist that Q is pure, and that's equivalent to saying that this CE is always equal to 0. If psi is a basis for Q, then our orthogonal projection is simply the state of the orthonormal basis. B is just this, so then this becomes a P equals 0 implies and now for the main theorem of the entanglement measure section, we're now going to prove that the entanglement measure of a state psi is 1, i.e. it's completely maximally entangled state for all reductions down onto M systems, if and only if this psi is a basis of a error correcting code.
I mean, what's the line? If the state, like, why would you have a basis? Like if the basis that gives the density operator, or what? Like, where does the multiple vectors come from?
What multiple vectors?
Like the several phi's, like, because we were treating it's the linear entropy of a state, right? Like, where do these? The theorem is that if it's maximally entangled, like if we have the maximally entangled entanglement measure, then it gives an orthonormal basis. Or is that not? Maybe I understood it wrong.
Say that again.
That, like, if you have a state that gives the maximum for the EM,
yeah,
then it's the basis for some code.
Yeah.
Like, where do you get the basis from? Like the eigenvectors of the density operator? Because like the EM is defined on like a single state. Like, where do you get the multiple basis vectors?
No, there is no multiple basis because the dimension of the code is 1.
Okay. And it's just one guy.
One vector saving here because the dimension.
Okay. Right.
Then you see, this is where the notation falls down, doesn't it? Because, well, to be honest, though, they would normally, if it was more than one.
Yeah, but not always, though. Like, I see where I got confused, but.
And that's why it's just terrible notation. But I feel guilty that I've been using it because.
Okay, but you can never tell if it's like a singleton set or if it's a bunch of them that you just write them all the same.
They always everything's always just a singleton set, basically, isn't it, in their notation? So it's like you cannot denote a singleton set, and so the one time I needed to do it, which was now, it caused confusion.
Yeah.
Okay, so that means I can now get rid of all this because the only thing to remember is this. Yeah, if you've got an error correcting code, then for all Pauli operators t of weight minus d minus 1, this is 0. Okay? That's it. So it's very easy when you've got a one-dimensional curve. Right. Okay, so the entanglement measure on a subset on the subsets of M systems, M qubits of psi, is equal to 1, i.e. it's completely entangled for every single one, if and only if this singleton subset psi is a basis of a double brackets to distinguish the code N1 N plus 1 code. Okay, so let's just recall this means the number of qubits. I haven't used, so there's a stabilizer. So let's just say so if it were a stabilizer code, then this would be a 0. So this means the dimension is 2 to the 0. This means the dimension is 1. So that's the difference between the parenthesis and the quotiente. I don't know if I mentioned that before, but this means a one-dimensional code. So if it was a stabilizer code, this would be a 0 here. And then these do the same parameters as before. So D is M plus 1. So we've actually got two things to prove here. Yeah, so SV. Well, we've got to show that this is a code. So let's first say that E is an error. That E be a poorly operator. Wait. Okay, so what we need to show is that psi E psi is equal to 0, because then it will be, as we just saw in the previous board, a code. And the idea is to let S be a subset which contains what subset 1 to N. So we let S be a subset which contains the support of E. And by the support of E, we just mean the positions where the Pauli operator has a non-identity element. Okay? And we want to check that this thing is 0. Okay, so by the time we go over to the board, should be 0. So this is equal to its trace. We need that. Let me just trace. Well, I suppose, yeah. Well, this is equal to the trace of this. And you can see this step by going back the other way. So if you start with this and you calculate this trace with respect to an orthonormal basis, including psi, starting with psi, then you'll start off with this term being 1, and then all the others will be, you'll get the first term will be this term, and then all of the others will be 0. So in fact, yeah, we could have, in fact, you can just go straight here, can't you? So we could just go straight there. Okay, if you calculate the trace of this, respect to an orthonormal basis which begins with psi, then you just get this. And you psi by psi, you get 1 here and you get this there. Okay, so this is equal to its trace. So now we're going to trace over S and then trace over S prime of this. So we split the trace into over our sub things. But this E, so here, E does not affect the qubits in the S prime system. Since on the S prime system, it just has the identities. S contains the support of E. So this is just going to be when we trace out by so when we trace out by the S prime system, since it's maximally mixed, we're just going to get what we would have got if that E hadn't been there, because it doesn't do anything on that bit. We just get the identity on the S system times E, which is now restricted to the S system because the S prime system's disappeared. Okay? So so on the S prime system, E just has identity operators, so it doesn't do anything to the S prime system. So when we trace over the S prime system, knowing that we've got the entanglement measure equal to 1, we get a maximally mixed state on the S system, and we still got E there, but that's now just restricted to the S particles. And then as we've seen before, this is going to be 0 unless E restricted to S is equal to 1. In which case we don't have a, in which case so we're assuming that it's not the identity. Of course. Okay, so we managed to prove what we wanted to prove, that this thing here is indeed equal to 0. And therefore, from the previous blackboard, this psi must be the basis of a quantum error correcting curve, which is amazing because we know how to do this. So we're going to go back the other way to be amazing. So let's go back the other way. Yeah, this is slightly more tricky. Now the Paulies form a basis. So the Paulies, as we saw, all the operators form a basis. Now I want to write just E. Yeah, I want to write E. Form a basis. For all endomorphisms. What for the endomorphisms? So we our psi, this is going to be the sum over some constant times E, where the sum is over all Pauli's. And here we're going to use, but first we're going to try and calculate what this CE is. So if we multiply by m, this implies that m is equal to sum over in parallels C E M E. Just take the n. Right, so let's think about what you want to prove. Right, so now we take the trace. So the trace of m psi m, which as we just saw before is just equal to psi m psi, is equal to, and here we get the sum of CE trace ME. But these traces, as we've noted before, the trace of all the power is always 0 unless it's the identity. So this will just give us CM times whatever the trace of the identity is, which is 2 to the how many? We're now just over the big system, aren't we? So that's 2 to the n. Okay, so what this implies that this ket bra is the sum of 1 divided by 2 to the n. Changing now the n to an e, to put this into here, times e, and we're still summing over all the e's in the powers. Right, well, that hasn't actually done anything yet. That was just working out what the C's are. Well, we do know now we know something here because we know that which we're proving the backwards thing, yeah? So we're proving the backwards thing, so we know that we've got an error correcting code. So we know these things are 0 for the up to the n systems. So this is 1 over 2 to the n times the identity plus the sum, and now the weight of E is going to be at least m plus 1 times, okay, so we're just using the fact here in this equality that this psi is a basis of an error correcting code. So all of these coefficients here for the Pauli's of small weight will be 0 by the definition of what it means to be an error correcting code of dimension 1. Right, now for the clever bit, I think. So we need to prove that so we need to prove that if we trace out, so let's say we need to prove that for any, yes. Well, it's better to say this, let's say length. So let S be a subset, and we need to prove that the linear entropy of the reduced density operator, goodness me, difficult to say, is going to be 1. So let's see if that's the case. So that S be that subset, and again, S prime is the complement. We're going to trace out, so rho S of this is the tracing out over S prime of all of that. So let's just do a little check here. Hopefully it's already fairly clear what's going to happen, but let's just do a check. So let's say without this generality, this is 1 to n. If we're tracing out the n plus 1 to the other bit systems, we're just going to get the product of the trace of sigma I from I is n plus 1 to n times the ones that still left. Sigma 1 to z to n. But if so there must be a I in n plus 1 to n. Is equal to 0. Because the weight of this is n plus 1, so these n may not be identity elements, but there's got to be one which is not an identity element in here. And the trace of the non-identity poorly is 0. So we're going to get a 0 here, and all of these things are going to be 0. So this is equal to so that's just a balance of going. So we'll see that argument works for any subset of size n. So we have to trace here, so then we come back here, so this implies that rho S rho psi is the trace over S prime 1 over 2 to the n times the identity. And this has n minus n particles, so this is 2 to the n minus n divided by 2 to the n, which is 1 over 2 to the n. Which is what we wanted to prove. So this is true for all subsets S, which implies then if you then put this into I'm a bit confused. Oh yeah, sorry, I missed out. I'm tracing up the S prime, so there's an identity on S of course. On the S system left. For also says S, so this implies that the entanglement measure then. You should watch out before. There is widely from only if all the reduction Hamiltonian systems were maximally mixed. Is that all right?
Yeah, makes sense.
That's cool. So we know how to make these things. Well, we know how to make some anyway, because we saw in the exercises a 604, which implies that exists a maximally mixed. So they call it army state, AME, absolutely. Or any 6. Oh yeah, I should have said so. So since M is so we have M was less than or equal to, sorry, M is 3. This is less than or equal to M divided by 2. And we missed that from the Schmidt composition. And if it's actually maximally entangled on M, then it's actually maximally entangled on M minus 1, M minus 2, and all the systems going down. So that's obvious, no? Because if you go down to the 3 systems and already you've got all identity, if you trace out any more, then you're simply still going to get the identities. Okay, so you're really looking for army states, the best ones, the crown jewels are going to be ones where N1 2 plus 1 exists if only if N is 2. That was the Bell state. There's 1 of 3, there's 1 of 5, and there's 1 of 6, which we all saw in the class. Yeah, so this N is 6 as a stabilizer code. So there's a stabilizer code coming from a matrix by 6A, where A is the adjacency matrix. Sorry, the incidence matrix. No, the adjacency matrix. Of the wheel with 5 spokes. Okay, so I've got Edgar busy looking at that. He's also looking for, since we've only got entangled states for these values are then for qubits, what we do is we look for systems over larger spaces. So instead of looking at states in qubit samples, where instead of having C2 here, we have CD. Okay, now the Paul is generalized in a very natural way. Well, in fact, in a natural way, but not in a unique way. so necessarily. But you can set up various different nice, what they're called nice error bases for your endomorphisms using variants of the Pauling operators. And pretty much everything we've done, and certainly in error correcting codes, in entropy, and here again in entanglement, you can then do with this new set of Pauling operators you've got on these systems. I've only got like half an hour left because I want to give Hector 15 minutes, 10, 15 minutes at the end just to do his problem because he won't be able to do it on Thursday. So I probably won't go into that now because it's just basically straightforward. And we don't need it. We also don't need what I'm about to say either, but anyway. Is there anything else I wanted to say there? Oh, yes. And the important thing I wanted to say was we've now proved the singleton bound for K0. So the model of this is that which is the singleton bound. With K equals 0. Okay, so recall that this is equivalent to, in our notation, N0D. And we proved for an NKD that N was bigger than 2D minus 1 plus K. But we did prove for K0. But you see now that it follows from this. Because of theorem, there is this sign such that EM was, so this would be ED minus 1. Which implies, since we know that n has got to be less than n equal n divided by 2, okay, so we get a singleton now for free from that, which implies, which makes me think two things. Firstly, that somewhere, and this is what Felix said, he said, well, for K0, it comes from the Schmidt decomposition. Yeah, probably. So you should be able to prove this directly. This singleton bound directly from the Schmidt decomposition, because that's basically all we've used to prove this theorem. Yeah, and the other thing it made me think of is that maybe there is a proof of the singleton bound where we had to do that kind of cheat thing where we said, oh, the A and the R systems are uncorrelated. Maybe you just have to trace out carefully with the B and C system and really write out the things over, write out the density operator over the Pauling basis, like we did in the proof here. And then maybe you can make it work. I think probably, yeah, probably you can make that work and you see that you can factorize out the A system. Okay, how much time have we got left? Right, let me see if I can tell you something at least very, very sketchy about quantum supremacy. So at least you know what it is they're talking about when they talk about quantum supremacy. Well, the general idea is the following. I mean, you want to build a quantum computer which is better than a classical computer. How are you going to prove that? How do you prove that your computer is better? Well, the idea is to look at quantum circuits. So we've seen a quantum circuit on n qubits is defined by a unitary matrix. And this is a huge matrix. Okay, and so to implement this this unitary matrix, you need a big classical computer because you're going to be 2 to the n. You've got this 2 to the n. The vectors have got size. Have got 2 to the n coordinates. That's 2 to the n complex numbers. The unitary matrix more, and so it's going to be very difficult to. So even for n equals 50, which is what they use more or less in the Google demonstration, this is impossible to implement on a classical computer. But imagine somebody we have to implement it as best we can. So we implement it the best we can on a classical computer, the best classical computer you can find, and we also implement it on our quantum computer. We also implement it on our quantum computer using fault tolerance, quantum codes to the best of our ability. The best of our ability. Okay, so we want to be able to compare these two implementations of this randomly chosen unitary matrix. Now, to be able to compare this, we have to do a measurement, because if we don't measure, we just don't know what our quantum computer, the output of our quantum computer has been. So we implement and we measure with respect to the computational basis. And measure x. Well, let's just say x in with probability. How does that be? X. Yes, so I have to say, it was defined on a unitary matrix U starting in state. And let's say it starts in state size 0. Okay, so we implement it to size 0, so this will be U size 0. Okay, so that will be what happens if we on our quantum computer. Okay, so we've got a quantum computer, we initialize one state, we apply a randomly chosen U, and then we do a measurement with respect to the computational basis, and we'll get this probability. So this is going to be some probability P from, let's call it P quantum computer. Yeah. No, I don't know too much about next here because it doesn't really depend on which element of the computational basis you have. Yeah, since we've chosen our our unitary matrix at random. We do the same for our, so on our classical computer, and this will output some string of 2 to the n bits somehow, and we simulate a measurement on that. So I'm going to really say simulate a measurement. To obtain, well, yeah, it says, yeah, P classical, what do I call this? CN, classical X, okay, in the same way. Now, this is the important, there's 2 bits of important bits. If you was a classical function, just a function from 2 to the n to 0, 2 to the n minus 1 to 0, 2 to the n minus 1, and you chose it at random, then obviously you would get any kind of output on 0 to 2 to the n minus 1 with probability 1 divided by 2 to the n, so everything would be like a uniform distribution, and there wouldn't be anything to do. But with a quantum implementation with a unitary matrix, this is not the case. There's probability distribution. So if we repeat for many unitaries, we get a continuous window variable x. So this x is just going to give us what yeah. I probably should have said before I said that last sentence. But let's imagine we had a perfect implementation. So suppose we had a perfect implementation. And repeat for many u, then we get some random variable x and some continuous variable x. And surprisingly, and this is not obvious, so probably shouldn't have said that there. This has a calculatable density function which we can calculate, which is not going to be uniform. Okay, so it is not uniform, and the reason being, now to prove that it's not uniform, I'm going to cut some corners. But I'm going to tell you one thing, that so what we want to do is the probability we want to calculate. So a randomly chosen we will put a random state. Random state. I'm going to write the coefficients here as real numbers. So x is going through 0, 1 to the n, and the ax and bx are 3. Okay? So the probability that we measure, so the what's the probability we measure x is going to be x squared plus bx. So if you want to know this would be P. So what's the probability that X is kind of P? What's the probability? Well, it wouldn't be unreasonable to try and count all the states for which this is equal to P and divide it by all the states which are states, which are really the sum of all the ax squared plus bx squared is equal to 1. Okay, so we can estimate, well, we can calculate it. Now, what is all the states which going to give probability P by V? Well, what's all states first, because that's a bit easier. What we want to do is integrate over the all of the x's, and we only want to take out the x's where the sum. Oh, there should be the sum inside. Oh, I didn't bring it with me. I think that's a little mistake there. That should be. Oh, that is. Oh, I see. Yeah, okay. Yeah, this is just to say you integrate over all the ax and bx's. So this little project means this is then integrating over 2 times 2 to the n variables. You want that the state is normalized. And that's it. Okay, so that will give you the volume of all the normalized states. Whereas here, we do the same thing. We got this delta. And then we've got, let's say, measuring 0 would just be a squared plus b naught squared minus p. Okay, so let's just have a look. So we're trying to calculate the probability that this is going to you measure 0, repeating the unitaries many times is going to be p. I claim it's vp divided by v. Now, that's not obvious, and to prove that, you have to prove that the unitaries can be selected at random using the Haar measure, and that's also not very easy either. So I'm going to skip over that. So I mean, logically, it makes sense that this is a pretty good way to calculate it. So here, this just picks out the bits where this is 0. Yeah, 0 unless what's in here is 0, in which case it's integrally 1. Yeah, have you seen that before somewhere? The physicists, I'm not sure I've seen it. So this is well known to be 1 divided by 2 pi. So this is just this. Okay, which is just all this is doing is it's putting everything is 0 unless this is what's inside here is equal to 0. In which case, when you integrate it, it integrates to 1. Okay, well, let me skip over all these integrals. So I was going to tell you exactly how these things get integrated. But it turns out that actually it's not that difficult to integrate these things. You have to, so we can integrate these things. One of the tricks, of course, is to use the fact that this x squared becomes x squared here, and then you're just integrating over what looks like a bell curve. And you know what the integral of that is. So it turns out that V is pi to the n divided by n minus 1 factorial. Here n is 2 to the n. And Vp is pi to the n divided by n minus 2 factorial, 1 minus p to the n minus 2. So this implies that the x has a density function which is n minus 1, 1 minus p to the n minus 2, which if at n large, asymptotically, is this, which is extraordinary. So just to finish, so now you've got your distribution. This is the distribution you would expect if you had a perfect implementation, but you don't. Neither in the classical implementation, and probably not either on your quantum computer that you've built. But you can use it, you can compare it to what you've got on the distribution you get from your implementations. And that's the clever bit. So you then use this, so now you know what you would get, the distribution of probabilities you would expect if you could implement everything properly. And you kind of do this kind of cross entropy, similar to what we saw in the Klein inequality. So as in Klein, we compare output implementation with this perfect implementation. Now, the only slight problem here is that our implementations give us a discrete random variable, and this one's give us continuous. So we didn't just calculate continuous, but so you have to make some approximations. But the idea is you calculate minus the sum over x in 0, 1 to the n. So this would be what we get from our implementation, and then we do it log p of x, and this is our perfect implementation. Okay, so we set up this quantity, and we can calculate this for various implementations. So this is our implementation here. So the trick is to move from this continuous to the discrete, because this should be discrete, unfortunately it's continuous here, is to use the fact that the sum over x of f of f of q. So we can replace here. So now let's try and do one of them. So if we did nothing, if we did the most, if we implemented classically and got simply, so if we really didn't do it very well, then the worst case we'd get P of x is 1 divided by 2 to the n. And now you can just calculate that. So this is, So this was H worst case. This would be the minus yeah, I think this should be minus 1 to the n. Minus 1 to the n, then we get the n from here, and now we can just do the expectation of the logarithm, which is this, then we get some of the, this is not here. So the density function times the logarithm of p. Okay, so you calculate this, and in the worst case, this turns out to be log n plus e. That's our e 2.71828e. And in a perfect implementation, so if we actually have the perfect implementation here, then you see we would have the sum of p log p. So in H best case, this would be minus 1 by n, the integral sum of 0, and the density function, and then the expectation of what we got here, which is p log p. So then it would be p log p, or in favor of p. And if you do this, then you get log n plus e minus 1. So now we can compare really bad implementation where we just get probabilities 1 divided by n, and perfect implementation. And they're different. So what we do is we implement and we compare. So yeah, so this is called, let's call this H implementation. So then we let, just to make things look a bit nicer, so we can, what do we call it? Yeah, so 1 bigger than H, worst case. Okay, so we take, whatever implementation we get, we take it away from the worst case, which was log n plus e. You see, and in the best case scenario, then, best case we get 1. And if we put worst case here, then of course we get 0. So we get that this quantity is always between 0 and 1. And this is going to be the n then. So we have quantum supremacy. And H. So let's pull this up again. Well, this is better than the best classical. So this alpha for the quantum computer implementation is strictly bigger than the best possible classical implementation. So it's got nothing to do with factorizing extremely big numbers. It's just implementing a randomly chosen unitary matrix. So I hope that's giving you just kind of like vague. I went a bit quickly and I skipped over the details, but I just wanted to show you a little bit of. If you look on arXiv, lots of interesting articles that you should now be able to read about various different things. I'm going to stop the recording now because Hector is going to do his solution, if he's there. Yeah. Is that okay, Hector?
Yeah, well, you can record if you want. Since I won't come on Thursday, I don't care.
Okay. All right, let's keep recording. I'm going to sit down then. You start when you're ready.
Okay. Uh, mm, mm, mm. Can you see my screen?
I can see me, yes.
Fine. Okay. So this was the problem. Suppose rho AB is a pure state, it's psi for some psi, and in the where psi is a state in the tensor product AB, and then prove that psi is a product of two pure states of each space CA CB, if and only if the entropy of rho A conditioned to rho B is smaller than 0. I think this is conditioned entropy. Is it right, Simeon?
Yeah.
Okay. So, well, what we do is using the Smith decomposition we have seen in class that if we have a pure mixed state, then the entropies of both subsystems are the same. And also we know that for pure states in any systems, the entropy is 0. And well, if applying the definition of conditioned entropy, this entropy is the entropy of rho AB minus the entropy of rho B. But since the entropy of rho AB is 0, this is just minus the entropy of rho B, and minus this is equal to minus the entropy of rho A, since these entropies are the same. And so we notice that the conditioned entropy is always smaller or equal than 0, and this happens because we are in a pure mixed state. Okay, and now we will proceed to do the proof, but it's easier if we not negar in English.
If we don't rule out, what do you want to say? We want to do the negation.
If only if B, we will prove no A if and only if no B.
Yeah, the negation. Yeah.
Okay, so and this is what we do here. And the negation of C different is psi equal to CA times CB. If and only if this would be greater or equal than 0, but since we know that this is always non-positive, this becomes unequal. Is it? Well, I think it's fine, and yeah. It should be. It's quite easy. And then the direct implication is easy because we just calculate the density matrix of the composite system, and with this we can calculate the density matrix of each subsystem, and it's just CA CA and CB CB, and the entropies of these are 0. So the condition entropy, we have seen that it's minus the entropies of this, and it's 0. So this implication is quite easy. The difficult implication is the other one. And for the other one implication, we start supposing that this entropy is 0, the conditioned entropy, and this implies that the entropies of both rho A and rho B are 0. Okay? Since the entropies of the subsystems are 0, we can suppose that the subsystems are, well, we know that the subsystems are in a pure state because the entropy is 0 if and only if we are in a pure state. And so we can write rho A and rho B in this way. Okay. And we want to prove that this implies that the state of the composite system is this one. And is it clear? Well, I hope so. And how do we do that? We take these vectors CA and CB and extend them to an orthonormal basis of each of the spaces. And this is what we do here. And with 1A is CA and 1B is CB because we are extending the basis. And since the product of basis is a basis of the tensor product, we know that we will be able to express psi as a linear combination of elements of this basis. And what we will prove is that this linear combination, in fact, only contains one element that is the 1A, 1B, that is CA, CB. And so we will see that the rest of the elements are 0. And C11 is the only non-zero element. How do we do that? We calculate the density matrix of the tensor product like this. And well, we get this expression. It's a double sum over 2 i's and 2 j's. And with this, we can calculate the density matrices of each of the subsystems, and we get these expressions. And now the thing is that we already knew the density matrices of A and B, and so we just have to compare these two expressions with these expressions. And comparing this, we will get some equations for the coefficients that are these equations of here. And well, when you see these equations at first, it's a bit well. What I have done here, I didn't see it at first, but I think once you see it, it's not very difficult. You think of the matrix Cij, and this equation of here with I equal I prime and different than 1 implies that the row of the matrix Cij is 0. And so with these equations for I equal I prime different than 1, we can prove that all the rows of this matrix, but the first one, are 0. And with the other equation, we can, doing the same for the j's, we can prove that all the columns of this matrix, but the first one, are 0. And well, this implies that all the c's are 0, but the first one. And so, well, C11, this implies that C11 is 1. Well, it could be any complex number with modulus 1, sorry, but we don't really care about the phase. And with this, we get that psi is this, just the first element of this sum. That is what we wanted to prove. I don't know if it was clear enough or if I should repeat anything.
Does anybody want Hector to go a bit slower, or did it was? I mean, I just read through that this morning. It took me probably twice as long as it just took.
Do you want me to explain again something? Si quieres lo explico en castellano.
¿Alguna opinión? Bueno,
Si
lo
quieres
vas
lo
a colgar,
explico.
¿no?
¿Eh?
Lo vas a colgar en los ejes, ¿cómo se llama? El drive, ¿no?
Sí.
Vale, entonces yo lo puedo mirar. Está muy bien escrito y explicado.
Pero no me importa repetirlo si he ido muy rápido.
No, yo no sé, parece que no se quejan.
Bueno, lo tienen grabado, no sé. They can see the video if they, well, I don't know, whatever you want.